Well, hello there. So today we are going to talk about three-sat problem that we kind of introduced during the last lecture. So again, you have your 3CNF formula, which is just in the form of x1 or x2 or x5 and so on, right? So you have your formula, every clause has length at most 3, and you need to know if that formula is satisfiable. So for two-sat formulas, for two-sat we know the algorithm, we know an efficient algorithm, we discussed it the last time. For three-sat we don't know algorithm that doesn't run in exponential time. We also have a good reasons to believe that there are no such thing as a sub-exponential time algorithm for three-sat. But let's try to give it a good exponential time algorithm. The same thing we did for three-coloring, where we said, hey, we know how to do a 3 to the n algorithm, and then we did a 2 to the n algorithm, then 1.7 to the n, and then 1.5 to the n. So while those things are not, life-changing, it's not going from 2 to the n to n square, but in terms of performance, in terms of size of the instances we can handle, it's actually really good. Like if you have an algorithm that runs in 3 to the n and the largest instance you can deal with is of size 50, then if you improve that to 1.5 to the n, then suddenly you can deal with the instances of size, let's say about 100. So, those things matter. So for three-sat, we talked about it, and there is a 2 to the n brute force algorithm. So again, you just go through all possible assignments to all the variables. You say, hey, x1 could be either true or false, x2 can be either true or false, and so on. We have n variables, and to evaluate all the assignments and check if one of them is satisfiable can be done in 2 to the n time. And when we're talking about exponential time algorithms, I will just ignore the small factors, like, we also need to actually evaluate the formula, which could be done in linear time in size of the formula. Formula can be size up to n cube, because there are up to n cube possible different clauses, right? But when you have a term of the form 2 to the n, things like n cube are pretty much irrelevant. The whole performance is so dominated by the exponential factors that you don't really think about such things as small polynomial factors. Can we do better? And yes, we can. Yes, we can. There is a rather simple way to immediately improve that from 2 to the n to something a little bit smaller, and to recognize that we can look into one clause. So as I said, that when we're doing brute force, we can say, hey, x1 can be either true or false, x2 can be either true or false, and x5 can be either true or false. But what we definitely know is that they cannot be all false, right? So if I take this clause and instead of go through 8 possible combinations of true or false for those 3 variables, I can go through 7 feasible combinations, right? So I can go through combinations 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, and 0, 0, 1. Am I forgetting something? I think I do. I'm forgetting the 1, 0, 0. So those are 7 different combinations of assignment to these 3 variables. And then we can say, hey, is there another clause that is not dependent on those variables? Well, if there are no such a clause that doesn't have any variables from that list, then we're kind of done, right? Because after we assign values to those 3, we will have all the clauses that already have at least 1 variable substituted for some value. So it will reduce to a 2-sat formula at most, and we already know how to solve them. So you have to assume that there is some clause like x7 or x9 or x3 negated. And you can pick that clause and again say that, hey, there are only 7 possible combinations for them. So I can define my search space in a way of like just this grouping variables into triples. Each triple corresponds to some clause. All those triples are independent of each other. They do not intersect. And each triple can have only 7 possible combinations. So the whole running time would be, so the size of the search space is 7 to the number of, to the power of number of triples, which could be up to n⁻⁴. So it's 7 to the n/3, which is a little bit better than 2 to the n. So 2 to the n would be equal to 8 to the n/3. So this one is just slightly better. But it's, again, it's already improvement in exponential time. Like, so this algorithm is, the algorithm that runs in 7 to the n/3 is exponentially better than 2 to the n. While those both are not great, we can still say that that's a kind of a big improvement. So what we're going to do today is we're going to develop a better algorithm based on an idea we haven't seen so far. So what we are going to discuss today is an approach to solve problems called the local search. And the idea here is that you can take a point in your search space, and instead of like the brute force algorithm just take your search space and just take point by point and check all of them if they match your requirements. So we'll try to do something like that in terms that we'll again deal with the search space of all possible solutions, or like potential solutions, right? But instead of just picking them one by one and checking if they are, right for us, we can try to actively search for them. So we'll start with some point, and then we'll say, hey, this point is not great, and what I try to look for is a point close to it that is better than this one in some sense. So I'll try to find a node that I hope would be closer to the actual solution. So what I'll do, I'll go searching, like just every time, just changing my candidate, my potential solution just a little bit every single time. So I'm start like walking through this search space, not one by one, but just every time just modifying my solution a little bit. And then eventually hopefully I will find the actual correct solution. Sometimes that works just fine. Sometimes you can do sometimes what you can do, you can just start with any solution and start improving it, and you will end up with the best possible solution. That's called the greedy approach, that just like improvement to your solution will actually lead to the correct solution. That's, unfortunately, I don't have time to go through this approach. Please do yourself a favor and read on greedy approach, because it is fantastic. It has certain fascinating algorithms in it. But today we will discuss this algorithm for 3-sat that actually just kind of hoping. It's not guaranteed to that this wandering will actually end up with the correct solution, but we'll analyze it and see what we mean. But overall, the idea of local search is that we start with at some point, and then we kind of wander in some neighborhood of this point in some fashion, and try to find a solution. And if there is one, there should be a good chance that we will actually find it by this wandering. And then we pick another point by some algorithm that allows to pick point in the right way and start wandering there, and again hoping that we'll find the correct solution. So to do something like that, we first of all need to define what for two solutions, like for two possible solutions, for two assignments of trues and false to the variables, what that means for them to be close to each other, right? So, well, that is defined exactly how you would do that if you just had to pick one way to define it. You can describe your assignments of trues and false to the variables as a string of zeros and ones, right? Where we say that a variable, if the variable is true, then if the first variable is true, we put 1 into the first position of our string. Then if the second variable is false, we put 0, and so on, right? So And another assignment would be a neighbor of this one if it differs in just one location. So, for example, this one is equal everywhere except this point. So this is a point of difference, but the rest is the same. And what we'll do, we'll start with some point and we'll go to its neighbor. So that means that we'll just flip the value of just one variable. And then we'll flip it again and then flip it again. Well, some other variable, and then flip another variable, and so on, until we either find the correct assignment, or we would be doing that for too long and we kind of assume that we wandered too far away from our starting point. So let's see what that wandering would look like. So here is a plan. So we'll start with our starting assignment, and let's say it's this one. And we checked that it is not the correct assignment. So what we can do then is, well, if it's not the correct assignment, then there is a clause that is not satisfied. For example, x1 negated or x3 negated or x5. Right, so this is a clause that has this variable, and this variable, and they're all wrong, right? So what we know is that our assignment, if we flip one of those three, so you can pick one of them, flip it, right? So flip the value of one of those three and get closer to the correct assignment if there is one, right? So we know that we are wrong in one of those three locations for sure, because any correct assignment would have not these three values here. So what we do, we pick one of those three at random and we flip them. So let's say we flip this one. So now we have 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0. But now we can have some other clause that is not correct. For example, we can have x1 negated or x2 or x7. Right, so this, or this. And again, I can pick one of those three at random and flip it. So let's say we flip this one. So it becomes 0, 0, 0, 1, and so on, right? So this is our process, and we'll do that for some time, and then we either find a correct assignment, or after some number of steps that we will define later, we'll say, hey, stop, we wander for too long, and then we start it all over again. So the idea is that you start with your starting assignment, and then you like crawl around flipping variables that are in some unsatisfied clause. And if you did it for like t steps, you say, hey, all right, that's not a great run, so we can do it again. And then again. like sometimes we can like do this for a while. We can accidentally do the same as on one of the previous runs and then like differ, right? So this is like a graphical representation of what the local search algorithm does, right? So why is this any better than just going through assignments one by one? Well, as we discussed here, right? So when we're doing this first step, so we can get closer to the correct solution with probability at least 1/3. So we know that in one of those three locations, our current assignment differs from the one we are looking for. So we have 1 in 3 chances of getting closer to the correct assignment. So if it's like somewhere here, so this is the one we are looking for, right? So we can get closer and then closer again and then closer, and then we can get closer for a while and then just miss it and wander somewhere away from it. That can happen, but if the distance from my current assignment to the correct assignment is some number t, which is exactly for how long I am allowing my local search algorithm to wander around, right? Then on every step I had this like 1/3 chance of getting closer. So on following this path. So I had 1/3 chance of getting closer. And then next step again, I have 1/3 chance of getting closer. So getting closer meaning the distance to the correct assignment is decreasing by 1 every time. So in fact, in total, I will have a chance of 1/3 to the t that I will actually find the correct assignment, if there is one at a distance t. All right. So now my plan is the following. I want to somehow guarantee that my assignment is close to the correct one. And how can we do that? Well, suppose we know the correct assignment, right? So let's look at it. So suppose it's 1 0 1 1 1 1 0 0 1 1 1 0. It kind of sounds silly, but there are 2 possibilities. Either it has more zeros than ones, or it has more ones than zeros. So this has 1 2 3 4 5 6 7 8 ones versus 4 zeros. So if we draw the search space, you can kind of say that there are 2 polar points. One that has all zeros, 0 to the n, and one that has all ones, 1 to the n. The point is that if we kind of divide the space like this, so here we have all the assignments that have more zeros than 1, and this one have all the assignments that have more ones than zeros. So those are like light assignments and those are like heavy assignments, right? So your correct solution will fall into one of those categories. So this one falls somewhere here. So what we'll do, we'll use these like all zeros and all ones as my starting assignments for the local search. I'll start with one of them, and then I know that the distance from here to here is at most n over 2. So there are two possibilities. Either it's here or here, but if we got it right, so if we in the right half of the search space, then the distance is at most n over 2. So, and that brings me to how do we tie this all up? Well, we set t to be n over 2. So we will need to use this local search on 0 to the n and 1 to the n, use them as centers, do this repeated wandering many times, and then each time you wander, you will have, so if you have the correct assignment, then when I'll be processing one local search in 1 to the n, I will have 1/3 to the n over 2 chances of actually getting it right. So that would be a relief, right? Okay. So how many times do I have to repeat the algorithm if the correct chance of finding the answer is 1/3 to the n? We've already seen, I haven't showed you the proof, but the main idea that if something has probability p, then to know that this thing you're looking actually exists with at least constant probability, you need to repeat the process 1 over p times. So in this case, you need to repeat your search for 3 to the n over 2 times. So that is how many times you need to redo this local search thing in both 0 to the n and 1 to the n. All right. And 3 to the n over 2 is the same as square root of 3 to the n, which is actually a lot better than 2 to the n, and even this like 7 to the n over 3. So this is already better than what we had before. All right. Now we will think, how can we do this even better? Okay, all right. So how can we improve the algorithm we just described? Well, one thing we did is we found those two centers that kind of cover our search space very nicely, right? So we said, hey, we can pick all zeros or all ones, and one of them will be at the distance n over 2 from the actual one. But one thing you can argue is that you can actually pick a random assignment, right? You can pick a random assignment And with the probability 50%, the distance between your randomly picked assignment and the one you're looking for would be at most n/2. So the algorithm that we're actually discussing can be modified from picking all zeros and all ones and checking, doing local search for them by just drawing a random point and doing a local search from there. Another thing that you don't really need to do the local search again and again from the same point, right? You can redraw them every time. It doesn't really make a difference because, like, basically the philosophy here is that it might be that your initial point is just like too far away from the assignment you were looking for, right? And then all your repetition of your local search is just a waste of time. So instead we can also use like waste of time half of the time, but we can start our local search every time from a new point. So we can start from here and just wander around, and start from here and wander around, start from here, wander around, and if there is a correct solution, we will eventually find it, right? The other idea is actually a little trickier, right? So we can argue that you'd be closer to this point than n/2 with a reasonable probability. So there is a reasonable chance that you will be not in a distance n/2 but closer, and we can try to balance that with we can argue that our chances of being close to n/2 outweigh that we can do the shorter walks from every point, not n/2 but a little bit smaller. But that would only work if we are close, like, so we can do walks of size, so we can set t to be like 0.4n rather than 0.5. But then our local search will only work if we go to the distance 0.4. And the idea that you can kind of balance it, that yes, your local search would be, the conditions of your local search would be met more rarely, that you are not as often at the distance 0.5. Now, so you're not as often at the right distance, but at the opposite, the success of your local search will increase greatly, because the chances that you will find an assignment if you're at the distance 0.4n would be 1/3 to the 0.4n, right? Which is pretty good. So you can balance those things, and that will give you some improvement, but we will actually do one better. So the idea that is most exciting here is to be a little bit more relaxed about for how long I'm allowing my search to continue. It is kind of surprising, right? So while the whole philosophy was that I have my initial assignment, and I have its neighborhood, and I hope that my correct assignment is somewhere in this neighborhood of my current one. And then we talked that the distance is at most t, and every turn we have to get it right. Every turn we have 1 in 3 chance to actually go in the right direction. And then we have this 1. So if the distance here was d, then we have 1/3 over d to actually get there. And this is kind of this concept of being perfect every step is actually, like in real life, it's inferior to tolerate your own mistakes. So what we're going to do, so instead of saying that, hey, I want to go to my assignment as fast as possible and get there, and I have to be perfect every round. Every round I have to get closer, and that what gives me this like 1/3 over t over d probability. I will say, hey, at the end of the day, I just want to arrive here. So what if I will do something like this, right? So what if I'll wander for a little longer and arrive at the same spot? That would be, I would be equally happy, right? Also, it doesn't really cost me much. If I just allow my walks to continue a little longer, that would be enough to allow such a behavior, right? So that I will have a little longer routes to the correct solution. Moreover, I don't really care if my walk just wanders from this neighborhood and get to the correct solution. That's also fine. So while I analyze my algorithm in the idea that I want to get here, and in terms of the distance, I'm okay with getting actually pretty far from my original assignment and then hopefully getting back. All right, so that's how it works. So let me give you the motivation of why this is actually pretty good. So I have my initial assignment and I have the correct assignment. So the distance is d. Then every round I have 1/3 chance of going forward. So by that I mean that I made the right choice, and in my walk I actually got closer to the correct assignment, right? So I have 1/3 chance of getting closer to the end, and then another, and then another, and then I will get here. So then if I analyze it in this fashion as before, right, I will have 1/3 over n over d chances of getting there. Now, what about if I allow to do d plus 1 step? So now instead of doing just d steps, d plus 2, I'll allow my walk to continue for d plus 2 steps. Well, what I'm claiming is that now it would go something like this. So I will do some number of steps in the right direction. Then it could happen that I went back. I didn't went back in terms of that I went strictly to the previous assignment, but in terms of the distance, right? So if I flip the wrong variable. If I flip the variable that was already set to the correct value, and I flipped it, and now my distance actually increased by 1. So I had 2/3. Let me actually write it here. So at this point, every time I have to assume that I have probability 2/3 to actually increase the distance to the correct thing, to the correct assignment. So then the probability will be like 1/3, 1/3, 1/3, 1/3, then 2/3 to increase the distance, and then I have to hop back again with probability 1/3. So the chances that my walk in terms of the distance to the correct assignment would look exactly like this would be 2/3 times 1/3 to the d plus 1. So which is a little bit worse than this. So we actually lost some probability. But this hop back can happen not only here, but it can happen here, it can happen here. I don't care, right? So if you analyze how many, like what are the chances of having any sequence of hops that include one hop back, it would be actually d times 2/3 times 1/3 to the d plus 1. So I actually increased my chances if d is big enough greatly. So what I have actually, so if I divide those things, so my chances increased by d times 2/9. So if and as we said, we think of d is some fraction of n, so and n I suppose is a pretty big number, otherwise that wouldn't be an interesting thing. So by allowing just one hop back in this walk, I increase my chances by some fraction of n, which is amazing. So it turns out that I actually can allow a bunch of hops. So what I do now, what the algorithm does is it starts at a random point and it does this walk of length n and hopefully finds the correct solution. So if you analyze, like, you actually need to crunch the numbers and do the calculations, but if you do that, if you analyze what are the chances that you started from the random point, and if you take into account what would be the distance to the correct assignment, right? So what is a d? What is a distribution of possible d's? And then what is for each d the chances that this walk of n steps at some point will go through this assignment, which would go like this. Every step we have this 1/3 chance to getting closer and 2/3 chance of getting further away. So if you actually crunch all of those numbers, you will get an algorithm that runs into 4/3 over n, which is actually amazing. So this algorithm that does this fantastic thing of just like pick a random assignments and start doing random things to it. Like, there is nothing complicated about this algorithms, but all the complexity actually lies into the analysis. again, this class is pretty heavily hand-wavy. I'm not interested of giving you the very specifics of how things work, but rather than let's explore how beautiful are those ideas that goes into the algorithms. So yes, this is the algorithm we actually can analyze and get that the running time is 4/3 to the n, which is so much better than everything we've seen so far, right? And yeah, so this is the local search based algorithm for 3SAT, and I hope you enjoyed it.